Hello everyone and welcome to another, well, we're calculusing. I have adventures for algebra, fun times for statistics, kumquats for calculus. Okay, I'm just going to cut that whole beginning. Here we go. So I want to talk to you today about an approximation method that I've used many times and is great for differential equations. So we're going to start off by doing some approximation. If you've never done approximation before, this might seem a little wild, but here we go. So suppose I know that dy dx is x minus y, and I know that when y input 0 for x, I get 0.5. We're not going to use the differential equation without solving. So I'm not going to do separation of variables. I'm not going to use the integrating factor method yet. I just want to approximate it without using those things at all. So I'm going to draw you a little graph here because I think the graph will help you decide what's happening. Yeah? We'll find out. So I don't know, like 1, and we'll make 1 really high up so that a half is easy to see, right? 0.5. There we go, because I know that at 0 it's a half, and there's 1. And I want to know what's happening at 1. Okay, so here's what I want you to think of. I know what the value is at 0. It's a half, yeah? So I know the value there, and I also know something else. I know that dy dx, so I'm using the things I know, is x minus y. But I have a value for x and a value for y, well, the resulting value when I put in 0. So I'm just going to put that in here. 0 minus 0.5 is 0.5. So what that tells me is, remember, dy dx is also the change in y with respect to the change in x. This is slope. So I know the slope is 0.5, which I'm going to write as 1/2 to help me out do this next part. Yep. Oh, I know the slope, so I know how it's changing. So I can draw out the slope here. So for every 2 units I go over in x, I go up 1 in y. So 1 unit over, 2 units over, and then up. So slope at that point. And I'm hoping you're seeing how I'm going to use this to approximate the value of y when x is 1. I've got this point. So I've got over 2 in x up 1 in y. Now my units I'm using here are half to make this 2 to 1, just to make it so that it reaches 1 here. And I'm hoping you see how I do this. So from this information about a value and how it's changing near that value, I can say that when y is 1, it's approximately, it looks like it's 1. This is exactly what Euler method is going to do. It's going to use slope, or the change from the differential, and some initial value point to estimate a value later. Now, you might be thinking, this doesn't seem very exact. I don't know if this is going to work. I agree with you. Let's see what the actual solution is. So let's use the integrating factor to do the actual solution, and then we'll compare our approximation answer we just got of 1 to the actual value. So remember, I started out with dy dx is equal to x minus y, so I'm just going to add y over to start because I need to make the integrating factor work correctly. And this is one that you can't solve by separation of variables, otherwise I would. So I'm just going to add y to both sides. The UPS guy is here, so my birds are losing their mind. I'm going to pause this for a minute. I am so sorry about that. That was very loud. Oh, and then I'm like an idiot, forgot to hit record, so I wrote the next step. Okay, so looking at this, hopefully you see that the stuff times y is just, a 1. So when we're finding our integrating factor function, we're going to do e to the integral of 1 dx, which will just give us e to the x. So that's what I'm going to be multiplying everybody by, is e to the x. Ugh, that looks horrible. So I end up with e to the x dy dx plus e to the x times y equals x times e to the x. So to start out with, I'm going to now use my big D notation. So this is going to be d sub x of e to the x y equals x e to the x. And then I'm going to integrate both sides with respect to x, because that'll undo my big D notation. Am I going to run out of space? I probably am. Okay, so on this side, integration of a derivative, those are opposite operations, so I just get e to the xy. Over here, I'm going to have to integrate by parts, so let's set up my parts. For u, I'm going to pick x. For du, or sorry, not du, for dv, I'm going to select e to the x dx. So when I integrate this, I'll get that v is just e to the x. When I derive this, or do the differential of it, that's what you're really doing, you just get dx. So that's kind of nice. So over here I'm going to have u times v, x e to the x, minus the integral of v du. So e to the x dx. When you integrate that, you'll just get x e to the x minus e to the x plus c. Don't forget your constant. So I need to use the constant to figure out what's going on. But before I do that, did not arrange this well. Let's take it up here. So you have e to the x y is x e to the x minus, not plus, e to the x plus c. I'm going to take everything and divide by e to the x, because that'll just leave me an e to the x on c. So I get that y is x minus 1 plus c times e to the negative x. Now what's fun about this is that'll make it a little bit easier to substitute in our constant. So just to remind yourself, because I literally forgot what it is, my constant is that when I put in 0 for x, I get a half for y. So I'm just going to move this over if it'll let me. Yep. This was horrible arrangement, Maya, so if you're like super judging me, I think you have the right to at this point. C, not E, C, E. I need to make these look different. To the 0, oh, that's going to be 1. That's awesome. Because then I just have a plus 1. What's C? It's 1.5. That makes it easier because you're just going to add the 1 to the other side. Okay, now I'm not done. I need to plug 1 into this. So y is equal to 1 minus 1 plus 1.5 times e to the 1, which when you calculate that, I'm going to have to approximate it. I'm going to shove it in a calculator real quick here. You get 0.5511819, and you're like, oh darn. The approximation we got earlier for y of 1, it's supposed to be a 1. Come on, 0. There we go. Ugh. We got was like, oh, it's 1. Like, these do not seem close. So you're like, I don't think so. That was kind of bad. Don't really like that at all. Well, as it turns out, that's a good thing, because the Eulers method that we're going to be using next is much better at approximating than what I just had happen. So it's very similar to what we just did, but at the same time, it's fast. And it's actually how your calculator, if it can estimate integrals or derivatives, actually does it. So if you're wondering where on earth you can get an approximation for a derivative or an integral, your calculators, if you have an advanced one, will definitely do it. If you have something like the TI-30, not so much, but if you've learned that in the past, if maybe you took AP Calc, or I don't know if Erin Simmons showed it to you, maybe she did, maybe she didn't, I guess we're going to find out in a second. It's actually how it does it. So it just uses Euler's method, because Euler's method is actually a real quick calculation once you understand what it's up to. So I'm going to scroll down and show you what Euler's method is all about. So this is going to take some visual and, yeah, it's going to require some visual methods here. Let me scroll this differently if it'll let me. Nope, it really wants to be picky about where it puts stuff. So Euler's method, the basic idea behind it is we want to use the dy dx slope to approximate y values. And what I want to emphasize for you as you do this is that this will work even if you cannot solve the differential equation. So that's what we really want to use this for, is the fact that this will give you a numerical approximation even if you've got something you can't solve by using separation of variables or the integrating factor, because there are differential equations out there that are not solvable by those methods. And so what this will do is it'll do that for you. So here's the idea behind it. So I'm going to draw you a graph. So we're going to have some starting value, which I'm going to call x0. Got it. And then I need a function that I want to approximate. I like to do my functions in blue. I'm just going to do something nice and smooth to make this easier for us to draw. Now, your function might not be nice and smooth, so keep that in mind. So here's the idea. At x0, I can go ahead and figure out what the value is. So I have this point, x0, y0. It's going to be my base point, the one I'm starting at. Okay? So we're going to be using the differential quite a bit for this. Recall that that doesn't look like a word. Sorry about that. When we've done the differential in the past, we've approximated a change in y using a dy. And dy was just dy dx times your change in x. Okay? So here's what we're going to do. What I want to do is I want to move a little bit away from x, just a little bit, and make a new point. So I want to use a different color for this point. Let's use orange because it's close to red. So you move a little bit away from x to a new point we'll call x1. How far do we move? A delta x, yeah? And so what I want to do is I want to use the slope at the previous value, so at x0, y0. So here it looks like my slope is about like that. We'll call it that. And what we'll do then is just what you saw me do a few minutes ago. We'll pick up this point. We'll call it x1, y1. Now, what's significant about this point is the y value here isn't exactly the y value we should get. What we should get is this y value. So the difference here, that would be a delta y. We want to estimate that difference using the derivative. So looking at, oops, I put my delta y in the wrong spot. We're going to use delta y as how far my y's are apart. Delta y. So here, this is going to be y1 minus y0. And it's approximately, you know, the change in y over the change in x from the function times delta x. And then all I'm going to do is I'm just going to add y0 over. Okay. Now, I'm going to add in one more thing. So this slope, this red line I specifically used over here, this was based at using this base point, not just any dy dx, specifically at this base point. So really, y1 was approximated at dy dx at x0, y0, because that's where I put in my slope, times my change in x plus y0. So then if I want to find my next step up, I'm going to use a different color for this so it's real clear where this is coming from. I go up one more delta x to x2. How am I going to find the value of x2? Well, I'm going to put in slope at y1, y0, which looks like I'm following the blue line here, so I want to be like about like this. Walk my x up, that's the y value I should get. So this will be x2, y2. What should the value of y2 be based on what we've seen so far? Well, it should be delta y, delta x at my new base point x1, y1 times delta x plus my previous y value, because I just added on to my previous y, which would be y1. So I'm hoping what you're seeing is using two slopes instead of just one like we did with my first example puts me closer to the actual value, because the actual value should be like right here. Yeah? And that's how we're going to improve it. Instead of just using one step with one slope value, we're going to use multiple of them. So this is called an iterative method because you can repeat it a number of times. How do you find the next one? Well, my next step of y is simply my slope at the previous step, xn, yn, times my change, however big I want it to be, that's a delta, plus the previous y value. So when you see the n's, I want you to think this is my next step after xn. So to find my next step. So as you look at delta x, I want you to be aware that if I chose smaller delta x's, so if I put my x's closer together, I could do this more steps and I could be more accurate because I wouldn't be going as far away. So the closer I can get, the more accurate this is going to be. So smaller equals better. Okay, let's do the one we just had, and that should help. Now, I have one caveat I want to add in here before we get started with that. For some reason, and I will never understand why your textbook does these things, and this is like a little warning, even though this is absolutely how you should be doing this, delta x, for some reason, your book likes to call h at this stage, even though literally we used this last chapter and called it delta x. I don't know. Just, you know, Don't cry. It's the same idea. Why did I say don't cry? That doesn't make any sense. So when I'm doing these, I like to do it as a table. So we're going to use Euler's method to approximate the indicated function value to 3 decimal places using h equals 0.01. And this is a very similar example to the one I just did. So I'm just making y squared. We're going to start at y of 0 equals 2, and we're going to find y of 0.05. So I'm going to set this up with just my n's and my x's first. So these are my xn's. Whee! And then we're going to figure out what the y-n's are going to be. So as you look at this, when I start, x0, the first step, is going to be xn is 0. And then the y for that's going to be 2. But as I move forward, my yn plus 1 is going to be, well, the previous y times delta. Yeah. So my delta, or sorry, not delta, dy dx. dy dx in this case is y minus y squared. And I would put delta x, but they're going to make me use h, 1.01, plus my previous y. So yn, the previous one, the one before it. So to do my first one, I'm going to move up by h, so 0.01. And then to do my second one, I'm going to move up by one more h, so 0.02. And then 3 will be 0.03, and then 4 will be 0.04, and then 5 will be 0.05. And this is where we're going to stop because we're trying to estimate y of 0.05. Get the idea? Okay, let's iterate our way through the y's. So at 0.01, I've moved up to the next stage. So my x value here will be the one from the previous step. So remember, when you're looking at the x and y in here, we're going to use the x and y from the previous row. So my x in the previous row is 0, my y in the previous row is 2, times my h, which is 0.01, plus my y from the previous row. I should have put n's here because that makes that a little clearer. Let's do that. Which was 2. So when you calculate all of that, you will get 1.6, which is kind of nice. So now I'm going to do it again. So for this step, I'm going to use the previous row's x, so 0.01, minus my previous row's y, which is 1.6. I square it, I multiply it by 0.01, and then I add the previous row's y. And you see how this starts to get a little messy because, so when you do this calculation, you will get 1.354. Now, I don't have to do the approximate symbol for this one because I'm not rounding, but in the next one I will. So I'm just getting in the habit of doing it now. So now I'm going to use these previous step, x value of 0.2 and 1.354 in this next step. So 0.2, this is me being lazy, but you know, 0.3 and 0.4 will be in the next one. So there we go. Minus, minus, minus. 1.354 squared times our h, which is 01. It's also called your step, plus 1.354. And you'll have to round this one. I'm going to round it to 1.91 since I said 3 places. I really don't want to. I want to carry it out to more spaces to make it more accurate. When you're doing this in your homework, you really should use more places to make it more accurate. So then the value I'm squaring will be 1.191 times our step plus 1.191 in our next one. When you do that, you will get 1.079. If this feels like something you can use Excel to do, you are 400% correct. Because I usually do use Excel to do it. It's just so iterative that it lends itself well to that. I keep wanting to put 0 first. Okay, so when you do that, there's no parenthesis here. I don't know what's wrong with me today. I'm making way too many mistakes. You get approximately 1.00, and I'm going to do a couple places here, 2.5. So what's interesting about that is you get almost exactly 1 by rounding. So I really should have written the right number of places. I'm going to get annoyed with myself if I don't fix this. So according to Euler's method, the approximate value of 0.05 is 1.003. Now, if you want, at this stage, you could go through and find the exact value solution to this one and prove to yourself that this is fairly accurate. Whew. Not too bad? Okay. Let's go on to the next one. Ooh la la. All right. So, I need to find y of 1. So this time I'm going to use h equal to 0.1 and pull up some technology to help you do this. So I'm forcing myself to do 10 steps because I want to, I'm only going to do the first few and then show you how to use technology to do the rest of them. So same setup, my n, got to do my x's, 0, 1, 2, 3, 4, 5, 6. Hopefully you know how many I'm going to need. If not, let's make sure you know. So I'm starting with x is 0, and my first y value is 1. That's coming from this point right here. My y next will be, I take my differential equation, which will be xn yn squared times my h value, which is 0.1, plus my previous y value. Okay. So my x's, I'm going up by 0.1, so this will be 0.1, 0.2, 0.3, 0.4, 0.5. Getting bored already. Hopefully you are too. 6. Why did I write that there? 7, 8, 9, and then the 10th one will be where I hit 0.1. That's the one I was trying to estimate. So 10 steps. Who doesn't want to do 10 steps? Me! Okay. So for this first one, I'm going to have 2, because that's my value of my differential equation. My previous y value, which was 0, times my new y value squared, times my h, plus my previous y value of 1, and that's unserendipitously going to be 1. Boring. Let's move on to the next one. So our next stage will have 2, our x value will be 0.1 this time, our y value will be 1 again, times 0.1. Oh, I forgot to square, gotta be careful, but 1 squared is 1, so you know how I am. I don't like to write ones if I don't have to and square things that aren't needed. All right, so for this one, we're gonna get 1.02. Who's ready to let technology help us? Me. Now I wanted to do a couple rows. Let's zoom this in a little. I want it to be easy for you guys to see what formulas I'm putting in. It doesn't zoom this part in. Great. Okay. This is going so smoothly. I'm very excited. Nope. So here I'm going to be putting my n's. Oh, that's right. My keyboard doesn't want to work when I'm like this. This is going to be interesting. N's. Here's going to be my xn's. And then here's going to be my yns. So I'm going to make my yns a little bit bigger too, because I want to have more space for that one. It's going to take up more space. So rather uninterestingly, actually, you know what? I'm going to pause the video while I do this and type in the 0, 1 through 3, 4, 5, 6, 7, 8, 9, 10, because we need to do that. Okay. So got my stuff typed in. It's actually kind of a good thing that the keyboard's being wonky and I have to pull up the touch keyboard, because then it's going to make it easier for you to see what I'm doing here. So to do this, you have to be clicked into right here, because that's what I want. And I'm going to do equals, and here's where we got to be careful. I want to use my differential equation, which is 2 times, where's the star? The value of, oh wait, I forgot to put my first row. Oops. Remember, good things, my y. Enter. I'm doing good at this today because I need my previous x and y to do this. So equal sign 2 times my previous x, which will be the one above it, times my previous y, times my value of h, plus my previous value of y again, so right up here again. So this is looking pretty good. Let's go ahead and hit enter. 1.02, that's good, because if you remember, that's what we got. Let's get the next row. And then, screw it, I'll just drag into all of them. Oh, it looks like it's like 2.333. Isn't that so much easier? This is me being very forceful in my assertion, except for I just realized I made a typo. I forgot to square things. Which you didn't notice because, you know, stuff. If I can go one day when I record these videos without having any errors, where is the caret key? There it is. That's how you square. In case you didn't know on Excel how to square. There you go. Enter. Okay, that one comes out the same, but this should be much bigger. It should be like 3 something. That's correct. Cool. 3.819 and some stuff. I have so much to cut from this video, I don't want to do it. Let's go. Now, on to some exponentials. This should be fun. Stuff. So, what's this gonna look like? Let's do 1.5. Ew. Well, oh, and I'm starting at 1. Let's just do h is 0.1 again, because that seems to be all I ever pick. Mm-hmm. 0, 1, 2, 3, 4. Hopefully you know there's only going to be 5. So I'm going to start at 1, then 1.1, 1.2, 1.3, 1.4, 1.5. Just a reminder, how I'm getting these is I'm just adding h. Cool. So this first y is also a 1. This sounds kind of boring. My next y is going to be e to the negative y, which will be negative 1, plus e to the negative x, which also happens to be 1 because I should have picked differently, times my delta h plus my previous y, which is also a 1. Now when you do that, you get 1.073573888, and that's when my calculator decided it hated me. So I'm going to show you how to make Excel do this again because I think it's just easier. There we go. So I'm going to use this worksheet to get this done. So I'm going to just do a new one. But actually, let me copy the first 5 rows because I can totally steal some of the things that are in this one. Copy. Cool. Next sheet. Paste, because I lazy. Paste special. Just paste. Now I have to be careful. I need to adjust my x's here. And I didn't show you how I got my x's last time, so this should be good. My first one's a 1, so I need to go ahead and delete some stuff. Enter. Yeah, it's going to change those values. We're just going to ignore that for now. 1.1, enter. And now what I'm hoping is that Excel will notice what pattern I'm going for here and then correctly, yep, it's going to correctly guess I'm going to go up by 1. So notice I just clicked and slowly dragged to see if it would come up correctly. Cool. So our first value of y is 1 also. Here's where we're going to have to do some adjusting. I need to change the differential equation. So the h value still stays the same, but this is not the same. So I'm just going to delete that and replace it with some parentheses because I'm a little worried if I don't do that I'm going to miss something. So if you've never used the Excel functions to do exponentials, this is going to be a wild ride. So it's exp for exponential and then a parenthesis, and now I need to put a negative y, so minus my y, close my parenthesis, and then add to that I need another exponential, so exp, open parenthesis, negative, and now I need my x, and then close my parenthesis. And we should be good. I'm hoping you can see that well enough to tell what's happening. I'm also going to attach this Excel sheet. And then I want to take this new equation I just made and drag it down to complete this. And that completes this problem. I hope you will use Excel to do this. I hope, I hope, I hope. Let me zoom this in more because it unzoomed it again. Well, that doesn't really help. Can you see the equation? I hope so. If not, I'm going to make this book available for you to download along with these notes to make it a little easier for you to do this. Cool. Time. Okay. Let's move on to the next one. Sorry. Ooh. Find y of 0.05. So I'm going to use Excel to do this. Again, not a shocker there. But at the same time, I'm also going to go ahead and use absolute error approximation. So I'm going to actually solve this and see what the solution is using not technology. So hopefully you recognize this first one is one that we can solve by using the integrating factor method. Or can I separate this one? Oh, I can separate this one. That'll be better. All right, let's do that. Because we haven't done any separations of variables in a while. So dy dx is equal to 4y minus 1. So what I'm going to do is I'm just going to divide both sides by 4y minus 1. That'll be a 1. So on this side, my integral is going to be 1 over 4y minus 1 dy, and on this side it's just going to be the integral of x dx. Let's go ahead and integrate that. So on this side I'm going to have to use u substitution. So I'm going to have my u, or I'll use w, be 4y minus 1. So then my dw, my differential, will just be the derivative of this times dy, which will be 4 dy, and then I got to divide by 4. So my overall integral when I replace will be 1 over 4, 1 over w dw equals to the integral of, I wrote x here, that's not correct. It's 1 dx. So let's integrate both sides. So I'm going to get 1/4 natural log of w, which I'll replace in a minute, equals, well, the integral of 1 is x, which is what I almost accidentally did earlier, plus c. So to solve for w, which I'm going to replace with y in a second, I'm going to just multiply by 4. So I'll get natural log of w equals 4x plus c. 4 times c will just be a new constant, doesn't matter. So I'll have the natural log of 4y minus 1 is equal to 4x plus c. I'm going to exponentiate both sides, so raise everything into the power of e, because that'll undo that, and I'll get 4y minus 1 equals e to the 4th x. We'll change e to the c to be a. This is a trick we've used a million times. Then I'm going to add 1 divided by 4. So y is going to be a e to the 4x plus 1 all over 4. Ew. I really thought this would turn out nicer. It doesn't. Oh, and I forgot my c. Oh, no, wait, it's over here. Sorry. And then I need to plug in the value to figure out what a is. What is it? 0, 1. So when x is 0, y is 1. So 1 equals a e to the 0 will be 1 plus 1 over 4. So you'll multiply both sides by 4 and then subtract the 1. So it'll be 4 minus 1, so a is 3. So overall, my solution is going to be that 3 e to the 4x plus 1 over 4. So if I want to figure out what a to the 0.5 is, I put 0.5 into this. When you do that, you get something close to 7. Yay. Let's see what the actual value is. Or sorry, let's see what Euler's method will tell us it is. So remember, that's our actual answer. Let's use Euler to do this now. So Euler's method, we got this. Let's do a new sheet, but I'm going to do the same thing. I'm going to cheat by copying. Why do I have to zoom in every time? It's because I'm annoyed by it. That's why. It's also going to be 5 steps because I'm going from 0 to 0.5. So let's make sure we pull up our keyboard. I want 0, enter, 0.1. Let's adjust our y. Nope, it's the correct one. It's 1. So I want to drag this down. Nope, it thinks I want to do 0.1. Oh, no, I want to make sure you know what series I'm doing. Cool. All right, so now we need to replace this with the differential that it actually is. So delete C. Ooh, I have one too many parentheses, so I got to be careful. All right, so I need 4 times the y value. And the y value was this guy, minus 1. And that's it. 1.3. Interesting. Let's drag it down and see what it comes out with. 4. Holy gosh, that's bad. Okay, so Euler's method says it should be 4.2386. Yikes. So if we wanted to approximate the error for this, what we should do is subtract the actual value from it. And since it's absolute value error, you should also do the absolute value of it. So it comes out positive no matter what. So if I take the answer that we got here and then say, hey, Euler's method was that I think this is 4.2863 and subtract them from each other, the absolute error. So I'm going to ignore the signs here because this should come out positive no matter what I do, thanks to the absoluteness. I'm off by like 3. That's not good. One of the reasons why this one is so far off is because, well, I'm looking at something that's linear in the y direction only, which is very steep, and that's probably why this is so bad. If I use a further smaller delta h, this will go much, much better. Let's do another one. This one ends up being more accurate. Okay, where am I at? Oh yeah. And this is another one you can solve by separation of variables, so I'm going to go ahead and do that. So I'm going to divide both sides by y, so we'll get 1 over y dy equals negative x squared dx, and we're going to integrate both sides. So I'm going to end up with another natural log. It's like I have a deep love of natural log. I totally do. And so y will be e to the negative x cubed over 3 plus c. Remember, addition inside an exponent is the same as multiplication on the outside. We're going to call this a e to the negative x cubed over 3. So there's our actual solution. We also know that y, when I put in 0 for x, will be 1, thanks to this base point. So we're going to go ahead and do that to figure out what value of a we get from this. I need to stop making that joke. E to the 0 power will just be a 1, so a is 1. Oh, I should have chose something more interesting. So y is negative e to the negative x cubed over 3. Cool. So in particular, I want to do y of 1. So if I plug in 1, y of 1 will be e to the negative 1/3. Oh, okay. And that's 0.716531306, using lots of decimal places on purpose. Let's go ahead and start doing some Eulers to this. Now, let's be a little more traditional. Let's do this the old way. X. What did I pick for h? I didn't say. So let's pick something big. So our x ends and our y ends start at 0. This is going to be whatever our h ends up being. I'm going to put that in later, times negative x squared y plus our previous y. Oops, I usually write y plus 1 so that I can do these as n's instead of n minus 1. Now I'm getting picky. So I'm going to start at the base point we have, 0, 1. We'll go up by, let's go up by 0.1, because that's what we've been using this whole time. So this will be 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 0.10, or 0.1.0. Wow. 10. Because that's what I want, is I want to know y of 1. Okay. I'm going to set up the first couple for these. So this first one will be 0.1 for h times negative x is 0 squared times 1. That's going to be nothing. Plus our y value, which is 1. Uh-oh. This might be some troublesome because this is going to be 1. But then at the next stage, it'll be 0.1 for our h times minus 0.1, because that's the x value, squared times 1 plus 1. So that will finally pull us out of the... I was worried this was going to spiral and stay at 1, because that can happen to you where it just doesn't move because it just gives you 1 the whole time because your x value never gets away from stuff. And this comes out 0.999. Oh, that's not interesting. Okay, let's pull up our Excel sheet and use it to do this. Dude. See if it remembers my paste. It doesn't, because that's my luck. Actually, I'm going to grab this first one because it's got, you know, the 10-ish steps I need. I know. Oh, I just realized it's only 9 because, oh, that's right, because I started counting at 0. Schwoops. What are you going to do? Does it have the right starting value? 1. Oh, 0, 1, so this needs to start at 0. Oops, let's fix that. Actually, I did need one more step. I need to pick this up and drop it down 1, and that starts at 0. Cool. Did I just not drag it down far enough? I didn't. So this one I actually never actually reached 1. I screwed up. Too late now to fix it, because I am not re-recording all this. You can't make me. Okay, so what do I need here? I need to change this. So my slope here, let's use some parentheses because I like them better. I've got negative x squared, so I need a negative here. Oops. Is that x? C2? Nope. X is b, so this guy times Stars. Okay. My y, and then let's close my parenthesis because that's my dy dx times my h plus my y. Looking good. Let's drag this down. Ooh, okay. 1.3000 and then 16. Is that close? It's not close. Why is this one no better? I thought this one was closer. Did I miscalculate this? Now I'm second guessing myself. It's happening a lot today. Maybe I shouldn't have recorded today. If you've been screaming at the screen the whole time, oh my gosh, that's not e to the negative 1/3. It is e to the negative 1/3. Well, my frustration is now through the roof. I really was hoping one of these would be close, and it's not. Okay, well, let's figure out our error. So I'll subtract this. I probably should have done more decimal places with the guy right here, but I didn't, so it's too late now. So our error ends up being 0.583. Oh, I have this in my notes. This one's also terrible. Why did I do two terrible ones in a row? I should have did one good one. Self-judgment increasing. Well, sometimes there's nothing you can do about error, I guess. Aw, I wanted to end on a happy note. Well, on a better note, errors and stuffs. Really, when your calculator does this, it doesn't pick something big like 0.1. It picks like 0.00001 so that it's stepping very small and very close and very accurate. So you don't have to worry about being so far away. I'm going to scroll back to the first page, so don't get blinded by this or dizzy. Remember this. How far off was I? I was hugely off. Why is this happening? Because at every step you get more error. Here I was closer. Notice here I was far away. Farther away. There we go. Words. That's what's happening. My error is propagating. Oh, that's why we don't use Euler's method for everything. Well, there's other methods out there that are better than this one, but there you go. Now you know Euler's, at least one numerical approximation for mathing. That's all I got for you today. I hope you enjoyed Euler's method. If you didn't, that's okay, you don't have to. But it's kind of fun to see how things are calculated, in my mind.